So, ladies and gentlemen, welcome to our seminar, this time at a very irregular place and time. And our today's guest is Harmender Gahlawat from IIT of Delhi, and he's our guest and collaborator. So, please.
Thank you. So today we'll discuss about this problem, T-cycle. I like this problem a lot. People call it terminal cycle and some people call it Steiner cycle. And we will study this problem on planar graph. This is a joint work with Meerav Zihavi and Abhishek Rathod. And so first we'll define what terminal loops are. So let's say we are given a set of terminals on a graph, and this set is a set of vertices. T is a set of vertices, and we call them terminals. And we say that a cycle is a T loop if all the vertices of all of my terminals are a subset of my cycle. And for example, consider this graph here. Let's say Z vertices are my terminals, and this is a cycle that passes through all of these vertices. Something happened. Sorry. It's not that. Yes. So yeah. So these are my red vertices are my terminals, and this is a cycle that passes through all of the vertices. Sharing is gone? No. Zoomed in. Yes, so I will very quickly stop the share and start again. Yeah. Slideshow. And now this should be. Okay, now is this the same file, right? Okay, now again, we are given a problem. In this problem, we are given a graph G and a set of terminals T. And our question is to figure out if there exists a simple cycle in the graph that passes through all of these vertices. Very simple. And this generalizes Hamiltonian cycle because, of course, you can make T to be the vertex set of your graph, and then you are just asking about Hamiltonian cycle. And this is well known to be NP-hard even for planar graphs. And also, assuming that exponential time hypothesis, this cannot be solved in 2 to the power little of n time for general graphs, and also cannot be solved in 2 to the power square root of n time for planar graphs. But good news for us is that this problem can be solved. The terminal cycle can be solved, parameterized by Trevet in 2 to the power Trevet time, which is very nice. Now, what we want to do, we want to solve this on planar graphs, and to do it on the planar graphs, we will use some techniques from the minor theory. I'll just very quickly say what minors are. A graph H is a minor of a graph G. If H can be obtained from G via one of these operations, either you can delete vertices, you can delete edges, or you can contract edges. And I'll not define tree decomposition and tree width for this audience. And I should not define parameterized complexity as well, but just I'll say for the sake of it that in parameterized complexity, you are for each instance I, you attach a parameter to this instance. And now you want to measure the tractability of the problem as a function of both the size of the instance I and this parameter K. And the well-established notion of intractability is W hardness. And the parameterized complexity of this problem is interesting. Already in 2012, we already achieved a randomized algorithm with running time 2 to the power K and linear in n. K is the number of terminals. K is the size of T. Now, and this is very interesting because since then, people have been trying continuously to get a de-randomized algorithm. And this is one of the open problem that is discussed again and again among the people who work parameterized complexity of terminal kind of problems. And it's notoriously hard to get, but some deterministic algorithm exists, and the best running time is 2 to the power some K to the power C. In fact, when Kawabayashi gave this algorithm, it was not 2 to the power K to the power C, it was 2 to the power 2 to the power K, but later Chujoy and Chekuri came up with this new grid minus theorem, and if you just fit the things, you can get this algorithm. Also for planar graphs, there was a deterministic algorithm with linear in K and log like polylog k, and it's n square time. And we would like to, it was wrong. So what you want, of course, like 2 to the power n, you can solve this problem. Yes, so it's n square, like it should be, like there is some bracket missing. It should be here instead of here in LaTeX. Okay, sorry. So another notion that we are interested in for this particular problem is the kernelization complexity. There is a notion of compression where you are given a parameterized instance, I and k. And what you want to do in polynomial time, you want to compress it to an equivalent instance, which is smaller. And the notion of smaller here is captured by that whatever you reduce to, its size should be upper bounded by some function of k. And then we say that we could compress our problem to a new problem, I prime, which notice that need not be a parameterized problem. It can be any problem. You can come up with any problem, and this is your compression. And if by any chance you can reduce to the same problem, you call it kernelization. So you compress to any problem, but if you can make this compression to the same problem, you call it kernelization. And whatever the instance you get is a kernel. Now, what we want in kernelization, there is a notion of tractability and intractability. If a problem is FPT, we know that it will admit some kernel. But what we want to achieve in kernelization is a polynomial kernel. You want that this size, that is f, function f, that captures the size, should be polynomial. And the notion of intractability is if it is unlikely to admit a polynomial kernel or compression, then we say that our problem is intractable. And this is a very interesting problem, terminal cycle, because this is the only problem, that natural problem, that is known to admit a polynomial compression, but a polynomial kernel is not known. We do not know any other such problem. In fact, already in 2013, what Wallstrom did, that they gave a compression of this problem to an algebraic problem, which is not in NP. So the compression goes to this problem of size k cube, but you cannot go back because this problem is not in NP. So we know that there exists a compression. But since then, it has been an open question that does this problem admit a kernelization? And people are going back and forth on this problem. And now most of the techniques that we know as of now to rule out polynomial kernelization also rule out polynomial compression. And people almost believe that these two notions are almost same. And this is the only problem that is a potential candidate for establishing this dichotomy, that these two notions may or may not be the same. Maybe they are different, but who knows? And when we started working on this problem, like every other people, our goal was to attack this question. We wanted to come up with a polynomial kernel for this problem, or establish that no polynomial kernel exists and, well, be very famous. But our plans did not go very well. So we backtracked a bit and we came back to planar graphs. So what we did for planar graphs, after working a lot, what we did for planar graphs is that we gave, this is our core result about planar graphs. This captures the combinatorial aspect, and all of our algorithms follow from this result. What we said, that if we are given an instance of planar graph, where G is a planar graph and T is a set of terminals, in linear time, linear in n, we can output an equivalent instance, G prime comma T. T doesn't change, and G prime is a subgraph of the original graph. So what we do, we take an instance, we get a subgraph such that the trivet of this subgraph is bounded by square root of k log k. So if we just plug in this into our algorithm, we get 2 to the power square root of k log k algorithm. And moreover, in this graph, we get a size set u such that if you remove this, and size of u is k log k, and if you remove this u from the graph, the trivet even goes to log of k. So, and this will be very useful in, second part will be very useful in getting the kernelization. And therefore, using this, we can prove that planar cycle admit a linear kernel. And also you can achieve this linear kernel in linear time. So for general graphs, we don't know, but for planar graphs, it admits a kernel. And this is interesting because other problems of the similar flavor are disjoint paths. And disjoint paths for planar graphs do not admit a polynomial kernel. And it does not admit a polynomial kernel for general graphs as well. And using this kernelization and whatever we spoken about, you can get an algorithm with running time 2 to the power square root of k log k and linear in n. So you can decouple this because of the kernelization. And now we'll come how to go ahead in these results. We will use the following planar grid minor theorem. We know that if we are given a planar graph and whose tree width is a bit large, or let's say 9 greater than equal to 9 by 2t, then you get a t by t grid minor in the graph. And this is a win-win situation. Given any planar graph, either you will get a tree decomposition or you will get a grid minor of this size. And this takes n square time. Now, why this becomes important? There is a notion of getting a sub-exponential algorithms. We wanted to get a sub-exponential algorithm, and everybody would think, the moment you think about sub-exponential algorithms, about bidimensionality. And this is a framework, well-known framework to get sub-exponential algorithms. And I'll just speak a little bit about it, and I'll explain why this doesn't work for us. So this is very suitable for problems admitting 2 to the power tree width and some log to the power c tree width algorithms. And our problem fits very nicely because our problem admits 2 to the power tree width. And just to take an example, let's ask this question. Given a graph G, does it admit a vertex cover of size K? And we know this problem admits 2 to the power tree width algorithm. And now immediately, if my graph admits 100 square root K times 100 square root of K grid minor, then its vertex cover will be large, at least 50K. So my instance is immediately no. So simply, we use this grid exclusion algorithm. You ask whether there is a grid. If you are returned a grid, you say this is a no instance. Otherwise, you are returned a tree decomposition of size at most square root of k, and you are very happy. You achieved an algorithm. But having a large grid, let's say some other problems which are good in this case. Let's say you want to find a very long path. Does there exist a path of length at least k? Of course, you can again run the same algorithm. If you have a very large grid, you have a very large path. But for us, because of the presence of terminals, a large grid minor can neither say a yes thing nor a no thing. You can have a very large grid lying somewhere and you can't say anything. This is useless to us. So what to do? And that's why for any of these terminal problems, as of now, there were no sub-exponential algorithms. For example, Steiner tree is in fact known to be the only undirected problem on planar graphs, which is natural and does not admit a sub-exponential algorithm. So these terminal problems they create problems. And for another disjoint problem, which is of the similar flavor, disjoint paths, in fact, we only got to single exponential 2-3 years back. So for these kind of problems, it was very unlikely to get sub-exponential algorithms, and we were thinking what to do. And then we looked into this technique, irrelevant vertices. So this was introduced by Robertson and Seymour to solve disjoint paths. And we say for a particular problem, a vertex is irrelevant if its removal does not change the solution. Whether this vertex is there in the graph or not, it doesn't change the outcome of my problem. So, and usually the goal is to delete the vertices so that finally you reach to a graph which has bounded tree width. And this was done for disjoint paths. But for disjoint paths, you can only get to a graph where the tree width is bounded by 2 to the power k. And that will give a 2 to the power k algorithm. And what we want, this 2 to the power k to be very small, square root of k. And here remains the challenge. Now, what we want is that we want our tree width to be little of k. And how do we do this? We again use some of the machineries that already exist. Let's say that we use a sequence of concentric cycles. We say that a sequence of cycles is concentric. I'll not define, better to look at the picture. These are just cycles such that each cycle is fully contained in the outside cycle and they are disjoint. They don't overlap in the vertices. And it's very easy to see that if you have a very large grid as a minor, you have a set of concentric cycles.
So does this definition work for general graphs or just for planar?
We'll use this just for planar graphs.
And you assume that you're given an embedding.
But embedding, you can, first of all, yes, you need an embedding, but you can get an embedding for the planar graph in linear time. Okay. Now, and it's simple, like it's simple definition. There's one cycle inside another. And if you have a very large grid minor, you have a set of concentric cycles. You take the outermost cycle of the grid and so on. And this bound is not very, it's not very difficult to see that this bound is in fact linear. And now the point is that if you have a very large grid minor, and this depends on the number of terminals, and then you contain a very large set of concentric cycles. Now, from these concentric cycles, some concentric cycles are interesting to us. Which of these concentric cycles are interesting to us? That cycles that do not contain any terminal. And for this purpose, we define something called a CL configuration. But again, don't go through the definitions. The only part is that these are a set of concentric cycles, which are many concentric cycles, and they do not contain any terminal inside. And now, if you have any loop, any T loop that goes through this cycle, a collection of this is like combination of these concentric cycles and this loop. I'm calling it loop just to differentiate it to these cycles. We call it a CL configuration. And in this CL configuration, we'll define something called anything that is inside, we call it segment. A contiguous part that is inside is called segment, and a contiguous part that is outside is maximal contiguous part outside is called out segment. Okay, so these green things are segments, and these blue things are out segments. Now, what we want to say that at some point of time, we will not have many segments of the same type. And for this purpose, we'll define the type of a segment. Everything will fall into place in a moment. So now, again, I don't want to define the type of the segments, but it's very easy to observe. So let's say that these segments, 4 segments, V10, V9, V8, and V7, they are of the same type. These are the segments which are parallel and do not contain any segment that has both of the endpoints between two. So for example, V2, V and V3 are parallel segment, but V2 and V1 and V3 and V1 these are not parallel segments. And for the same reason, V6 is not parallel with this U6, this segment, blue segment is not parallel with these segments. These are just the segments that are parallel to each other, such that on any of these portions, there is no completely contained segment. So these are just segments of the same type. And if you are very good with combinatorics of the trees or binary trees, say, if we bound the number of depth of each segment type, the type of segments is always bounded. Like the types of segments are bounded. It's not very difficult to see, because if you cannot have, to increase a segment type, you need to close it somewhere. And it, in the end, goes like a binary tree, and it looks like a reverse binary tree. I'll show the picture in a moment. But if you bound this part, that the number of segment types is bounded, the total number of segment types cannot be, like this depth cannot be too much. I'll come to it, what it is. Now, we define something called cheap loops. And we will argue about the structure of a cheap loop. And by the way, this is not particular to our problem. Disjoint path algorithms have been using it since forever. So what we say is that price of a loop is the number of edges it uses outside of these concentric cycles. So every edge that you get from this concentric cycle is free, but every edge that you get outside of this concentric cycle is very expensive. For example, these red portions, they are very expensive, because they are being used from outside of these concentric cycles. And we will say that if there exists a solution, there exists a cheapest solution. And we will argue about the structure of the cheapest solution. We'll say the cheapest solution will behave very nicely. And what does this nice mean? We'll say that if we have more than 3 segments of the same type, then my loop is not cheap. This cycle that this T cycle that I'm considering, if it goes through a segment, this set of concentric cycles, and in this, they create this more than 3 segments of the same type, my whole cycle is not cheap. You can get a cheaper solution. How do we do this? For this purpose, we have a lemma. Again, it's better to look at the picture than to look at the lemma. The point is that if you have three segments of the same type, the way these three segments, now forget everything else. Now only think about how these three segments will be connected from rest of the graph. Because of the planarity, there are very few ways you can connect them. For example, the way they are connected right now is not good. You cannot connect U1 to U2 and V1 to V2 because it closes the cycle. What will happen to this pink segment? Moreover, you cannot connect, for example, U1 to U3 because what will happen to U2? How will it connect to the other side? And with a little bit of effort, you will come to the point that this is a unique way you can connect these three segments from outside. These are the only three possible out segments. If you look only at these three segments and everything else is an out segment up to the symmetry, you can of course switch it. Now, what we will argue that if you have three segments of the same type, then this loop is not cheap. Why? This is the simplest part. Let's say this was your original cycle. Don't worry about it. You only have to think about these red parts. These are your segments. And why I have drawn it, just to let you know that although these other things look like segments, but for me, they are just invisible to me. I don't care. Like I'm just getting connected. I'm connecting U1 to something, U2 to something, and I'm just connecting these 6 points. And if I can keep these connections the same, I'm happy. I still get a cycle, and we will get a cycle from this. How we will do that? Now let's consider a point X on the innermost segment and Y on the outermost segment, which is on this cycle Cj minus 1. Since this is a cycle Cj minus 1, there is a path from X to Y. Now let's shortcut this cycle at U1, U2. This cycle is shortcutted at U1, U2, and you could go from U3 to U2 and you go via this. Like this is a very simple thing to do. It's not very complicated. You just deleted these two very expensive cycles. Since the number of segments are more than 3, they are using at least one edge, which is expensive. And since I have removed this part completely and no terminal is contained inside, this is why we needed, there is no terminal. These two portions did not contain any terminal. So what we did was, so we had these three my segments. They do not contain any terminal. This is my other part. This was my other part. This contained all the terminals. What I essentially did was I connected them in some fashion, and I again got a cycle. And this cycle does not contain the last segment, implying that this is a cheaper loop. So no segment, there cannot be more than 3 segments of the same type. And now, if you look at the segment tree of the type of segments, each segment type gives you one node of the tree. Although if you argue inductively, it's a bit complicated, but it's not very difficult to see that this will give you a logarithmic depth. The depth of this tree will be logarithmic. And hence, the total depth any of these segments can go to. So if this was your set of concentric cycles, the total depth that it can go to was some function of some order of log k. It cannot go deeper than log k. So all of these cycles, they were waste. I don't need these vertices, and hence we can delete these vertices. And this is what the core observation or core theorem is, that every vertex that is log k isolated, and a vertex being isolated means that it is separated. I say that a vertex is isolated if it is separated by log k many cycles to any of the terminals. So if all of my terminals are far, they are log k many cycles, this innermost vertex is irrelevant, you delete it. Simple. Now from here, you can get a first algorithm immediately. What is this algorithm? With the running time 2 to the power square root of k log k and n cube, you can get a cubic algorithm very easily. You simply ask for a c times square root of k, c times square root of k grid. And if you'll get this, you'll get some k log k grid, this which is marked as a block. And so what I'm asking is, I'm asking that each of these boxes is square root of k log k, square root of k log k. And if you get such a grid in the grid as minor, you get c log k small grid somewhere. And successful means you get a C log k, which do not contain terminals. And why I need these many? 10 times square root of k log k, 10 times square root of k log k. Because if you have these many, at least one of them will not contain any terminal. You have k log k many such grids. At least one of them, more than k many such grids, at least one of them will not contain any terminal. This grid itself has a very large size. You delete a vertex from here. So you repeatedly find such a grid minor. If you are successful, delete a vertex. If you fail, you go to square root of k log k. In each time to delete a vertex, you need n square time, because this algorithm required n square time, the win-win algorithm. And in total, you require n cube time. But now you want to get linear time. And that requires a lot of effort. What we want now is that we want to remove all of these isolated vertices in linear time. And let me just quickly. Okay. And for this, we use an approach of Reed, where what he does is that he cuts the plane in different parts in such a manner that each of the part, if it is, every vertex in this part is isolated from every other vertex on the other parts. So you cut the vertices, cut the plane in such a manner that every component will have a boundary with a hole. And this boundary, all of my terminals will be on the holes. And you can begin with such a configuration by simply making a very tiny hole close to every terminal. So each of these terminal will lie on the boundary, and you do something. I'll not go in details, not a lot of time, but you do something, and you can finally go into these small components. In the end, initially you have a plane with k holes, where each of the terminal gives me a hole. I will divide into k minus 1 holes, each of them into k minus 1 holes, and I keep going. And finally, I go somewhere where I have only 1 or 2 holes. And finally, you delete these vertices using some techniques, which are a bit too much. So the point is, like, other people have been doing it. I would just highlight the thing why it's a bit complicated for us, because for people who are doing it for the disjoint paths, they already want the trivet to be 2 to the power k. We want our trivet to be very small. So we want all of this they always can have this 2 to the power k factor. We want our time to be always linear in polynomial in k. And this requires some effort. But okay, whatever doing this, in the end, you will get these punctures, and the total number of vertices in these punctures, they will contain all the terminals, and the total number of vertices in these punctures will be some k log k. And these are the vertices that you delete in the vertices that I promised in the beginning. These are the vertices. And the point is, you get a subgraph G prime whose tree width is bounded. From here, it's easy to get an n cube time algorithm, but doing some work, you can get order n. And again, if you remove these vertices, your tree width is bounded by log of k. And here you do dp on tree width. And for kernelization, you use something called protrusion decomposition. What is it? So here you have your graph. If it has a modulator of size k log k, you can work a little bit extra to get a modulator of size k log square k, such that in each of the below components, they do not have edges among each other. They only have edges with the modulator. And there are very few vertices which have edges with the modulator above. And these are log k. All of these modulators have size log k. They only can have edges with above. Nothing else can have edges above, and they don't have edges among themselves. So if I can somehow maintain that between any of these two vertices, I know whether they can be connected from below or not without intersecting with other portions. So there is a problem called where you want to get a kernel while maintaining all possible connections. You want, given any pair of vertices from here, you should be able to connect them using disjoint paths. And if you can connect them using disjoint paths, of course, what will happen in the end? You will come, if this was your head, you will come, you'll go in and you'll connect these two vertices. This is the end goal. You want to collect these pairs somehow. And this will give you a cycle in the end. And you can keep all of these things, all of these connections using some work that again, I'll not go into. But the interesting part was why we really like this part is because this is not sufficient. If you do it immediately, you'll get a very large running time, but you want a linear time. The only thing to do now is that you do again the proto-regression decomposition in each of these components. And this is a trick. And this gives you the solution. So finally, the open problems, if you can generalize it to bounded genus or minor free graphs, or let's say it's a no instance, can you give me a cycle that contains maximum number of terminals? Or, of course, polynomial kernel for general graphs and deterministic algorithm for general graphs. And thank you.
Thank you very much. There is a space and time for questions.
Yeah, please.
So what about structural parameters? Is there anything interesting known or
Like we know that for you have a 2 to the power 3 with algorithm. I do not know of anything about, like we have a 2 to the power 3 with algorithm, also possibly a 2 to the power k algorithm. I don't know if people are expecting a sublinear algorithm for any of these, like sub-exponential algorithm for any of these parameters. And once you get 2 to the power k, I don't know if people are still looking for planar graphs. Again, once you get sub-exponential, I'm not sure if people are looking for.
thinking like kernel for vertex cover?
Yes, it admits a kernel for vertex cover. Yes, it admits a polynomial kernel for vertex cover. Yeah. Disjoint paths also admit a polynomial kernel for vertex cover. But this is the limit. Disjoint paths stop admitting kernel after that. Tree depth, path width, it does not admit. But I do not know about this problem. Also, like here, an interesting observation that was interesting to us. If you can get a polynomial kernel for k plus tree width, you get a polynomial kernel for k itself. Also, if you get a polynomial kernel for tree width, you get a polynomial kernel for k because you can bound the tree width to be polynomial in k. You can go to an instance. You can go to an instance where your tree width is linear in k or polynomial in k. Now, if you get a polynomial kernel with respect to only tree width, you get a polynomial kernel with respect to k. So even k plus tree width would be very interesting. But people will be very happy because k plus tree width will also give you polynomial kernel for only k. Yes.
Maybe a not very related question, but do you know if the problem of like given a planar graph with terminals and now we just want to cover it with the smallest number of cycles? Is that, do you know if it has been studied?
No, I do not know. And yes, we know that this has not been, I think that it has not been studied, and it can be a problem. Like we came across this problem at some point of time, but I don't remember exactly whether there was already a solution or not. I do not know if there is a solution. But cycle cover of the whole vertex set is a problem which is very well studied. You want to cover the graph using minimum number of cycles. You want to cover terminals using minimum number of cycles. I do not know. Yeah. So in case no questions, I thank you again.